In this video, we're going to talk about upper and lower bounds for sets and some related properties. So here is a definition. Let's let A be a subset of the real numbers. If the element U is greater than or equal to A for all elements A in A, then U is an upper bound for A. If W is the smallest upper bound for A, that is, if W is an upper bound for A, so here's our set A, and there's some stuff in there, and so there may be many different upper bounds. But if W is the smallest upper bound for A, then W is the least upper bound for A. So if W is less than or equal to every other upper bound for A, then W is a least upper bound for the set. And it's denoted in this manner. W is LUB of the set A. Similarly, we can talk about lower bounds and greatest lower bounds. So if A is a subset of the real numbers and B is less than or equal to A for every element of A, so here's some stuff in A. Here is B. If B is less than or equal to everything in there, B is a lower bound for A. And if G is an element such that G is greater than or equal to all of the lower bounds for A, then G is the greatest lower bound for A. And this is denoted GLB of A, greatest lower bound of A. So here are a few sets. The closed interval 1, 3, the open interval from 0 to infinity, and the open interval from negative infinity to 0. I'd like you to find just some lower bound as well as the greatest lower bound for the following sets, if such things exist. All right, so here we have the set 1, 3. This is a closed interval, so it includes the endpoints, and it's a subset of the real number line. And so, there's lots of things we could choose as a lower bound. For example, 0 is a lower bound. Whereas if we're asking for a greatest lower bound, what's a lower bound that is greater than or equal to all other lower bounds? That would have to be 1. So 1 is the greatest lower bound of the set 1, 3. How about the set from 0 to infinity? So we've got an open endpoint at 0 up to infinity. Is there a lower bound? Yeah, anything, again, lower than 0, or anything lower than this, let's say negative 3, is a lower bound. What's the greatest lower bound? 0 would be the greatest lower bound in this case. So 0 is the greatest lower bound of the set of open interval from 0 to infinity. So notice in the example above, the greatest lower bound was in the set, whereas in this example, the greatest lower bound is not in the set. How about the set 0 down to negative infinity? What is the greatest lower bound for that? Well, there is no lower bound at all, right? There is no lower bound in the real numbers. There's no one real number that is less than or equal to everything else. And so there is also no greatest lower bound for this set. Okay, here is another collection of sets, and for these I would like you to find both the least upper bound and the greatest lower bound for these two sets below. Now the first, 1 over n, such that n is an element of the natural numbers, and just recall, the natural numbers is like the set of counting numbers, so this is 1, 2, 3, etc., integers. This can also be written as the positive integers, is another way to write that set. And then the next set to do this for is n minus 1 over n, such that n is an element of the integers minus 0. Remember that the integers are the collection 0, 1, 2, etc., negative 1, negative 2, etc. So this is all non-zero integers. So pause, if you haven't already, grab a piece of paper and try to find both the least upper bound and the greatest lower bound for those two sets. All right, in order to determine these, let's just write out the elements of this set to see what the set looks like. So 1 over n, such that n is an element of the natural numbers. 1 is the smallest natural number, so 1 over 1 would be one such element. 1 over 2, 1 over 3, 1 over 4, etc. So this is what this set looks like. least upper bound. What's an upper bound for this set? Well, we can see that every element in this set, if A is in this set, then A is going to be less than or equal to 1. This is the smallest upper bound because 1 is actually in the set. So the least upper bound of this set, let's call this the set A. The least upper bound of the set A then is 1. And what about a greatest lower bound? So we can see that this is heading towards 0. This is converging towards 0, but it's never actually going to hit 0. So 0 is greater than or equal to A for every element A in the set. And we can also see that 0 is going to be the greatest lower bound. There is no lower bound greater than 0. There's no epsilon greater than 0, such that every element in that set is greater than or equal to epsilon. So the greatest lower bound of this set then is going to be 0. All right, let's look at this set. So this is over the non-zero integers. So if we had, let's say, n equals 1, then that would give us 0 over 1. If we had n equals 2, that would give us 1 over 2, 2 over 3, 3 over 4, and so on. And what about in the other direction? So we said that 0 is not an option, but what if n is equal to negative 1? Then we would have negative 2 over negative 1. If we had n equals negative 2, that would give us negative 3 over negative 2, and so on. So what's going on with this set? We see that 0 is an element of the set. We see also that positive 2 is an element of the set. Where is this converging to as we increase in n? This is getting closer and closer to 1, but never quite hitting it. What about in the other direction? This is also, so this is like negative 3 over 2, negative 4 over 3, etc. And this is also going to be converging to 1, just in the opposite direction. We never get below 0 or above 2. So that means that our greatest lower bound for this set, we can call this the set B, the greatest lower bound for this set then is going to be 0, and the least upper bound for this set is going to be 2. A set X has the least upper bound property if every subset of X that has an upper bound must also have a least upper bound. So the real numbers as a set has the least upper bound property. And this is actually just going to be an axiom, something that we assume to be true about the real numbers without proving it. You might think that this is kind of an obvious property that any set would have, but that's not the case. So for example, the set of rational numbers does not have the least upper bound property. So remember that the set of rational numbers Q is the collection of things that can be written as fractions. So m over n, such that m and n are in the integers and n is non-zero. And recall, we proved in proof 1 that the square root of 2 is not rational. So if we consider the set p over q in the rational numbers such that p over q squared is less than or equal to 2, then that's a set and it's a subset of the rational numbers. But we can see that, it has upper bounds. It has upper bounds in Q. So we're not thinking of this as a subset of the real numbers. We're just thinking about the rational numbers as a set itself. That's the big set X. So it has upper bounds in Q. For example, 10 is an upper bound. So 10 is an upper bound. There's lots of other upper bounds. But is there a least upper bound? We see that p over q squared must be less than or equal to 2. That means that, p over q itself is less than the square root of 2. The square root of 2 really doesn't exist in this set. But there is, if we think about this set, there's going to be this infinite sequence of values in this set that are getting closer and closer to having this property, P over Q squared, but we'll never actually hit it. So there's no one element in this set that we can say, there's no one rational number that we can say is greater than or equal to all elements in this set and is the largest such thing. So there is no least upper bound for this set right here. So the rational numbers does not have the least upper bound property. By assuming that the least upper bound property is true for the real numbers, you can prove the corresponding greatest lower bound property. So every non-empty set of real numbers which has a lower bound also has a greatest lower bound. Just to do some notation, remember Q is the set of rational numbers, fractions. R is the set of reals, everything on the real number line. We know that both Q and R are infinite sets. But we proved in proof 1 that the cardinality of R is greater than the cardinality of Q. Actually, we proved it in proof 2. So this is what we would call uncountably infinite, and this is countably infinite. This is also in our book if you want a refresher. And so that means that the set of irrational numbers, R minus Q, also has a greater cardinality than Q. So this is uncountably infinite, and this is countably infinite. There are more irrational numbers than there are rational numbers. And that fact makes the following theorem perhaps surprising, that between any two real numbers is a rational number. So let's prove this statement. Let's let A and B be two real numbers that are not equal, and where A is less than B without loss of generality. Then B minus A is then going to be greater than 0. And as we saw above, we know that the greatest lower bound of the set 1 over n, such that n is an element of the natural numbers, the greatest lower bound on that set is 0. So that means that there is some n in the natural numbers such that 1 over n is going to be less than b minus a. If that wasn't the case, then 0 wouldn't be the greatest lower bound, b minus a would be the greatest lower bound of this set. So there is some natural number such that 1 over n is less than b minus a. And now let's consider the set of m over n. So we're talking about this n right here, m over n such that m is an element of the integers. So that set, it's got, it's got like a million over n, it's got negative a million over n, etc. This is an unbounded set. This is unbounded. And because it is unbounded, that means that a, this value we had up here, so a is neither an upper nor a lower bound for this set. So A is neither an upper nor lower bound for this set. And so if we think about, this set, and it's got, like it's partitioning the real numbers into things of the form m over n, m plus 1 over n, blah, 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 forever and ever. And so where does A fall? There must be some place where A falls, and maybe it's between these, or maybe it's right on one of these, but A falls somewhere. And so there is some m0 there such that A is greater than or equal to m0 over n, but A is less than, strictly less than, m0 plus 1 over n. So in other words, we're saying, okay, we're going to say the place where this happens, we're going to call that m0 over n. This is m0 plus 1 over n, some specific integer, and that means that, okay, a is between those two values. All right, what does that mean for us? That means that then a is going to be less than m0 plus 1 over n, as we saw, which is equal to m0 over n plus 1 over n. And that is going to be strictly less than, okay, m0 over n, that's great, that's less than or equal to a, so we don't get the strictly less than from that. But we saw that b minus a was defined, we chose n, so that b minus a was strictly greater than 1 over n. And then what is this equal to? A plus b minus a, that's just b. And so what do we have? Then m0 plus 1 over n is in the rational numbers, and it's between a and b. So we chose two arbitrary real numbers, and there must be some rational number between them. So we've completed that proof. This theorem, that between any two real numbers is a rational number, has a couple of consequences. One is that, between any two real numbers, not only is there some rational number, but there's actually an infinite sequence of rational numbers in between those two real numbers. To see that that's true, we can repeat this process iteratively, the process that we see in the proof above, first with the real numbers a and b, as we saw, and then now with m0 plus 1 over n b, and then whatever we get from here, maybe let's call it m1 plus 1 over n1. We can repeat the same thing again, because again, this is also a real number, so we can find some rational number in between these two real numbers, and so on. And we can just continue doing this forever and ever. So we get this infinite sequence of rational numbers between any two real numbers. Also, this tells us that there is a rational number within any given distance of a real number. So if we let epsilon be greater than 0, be some real number greater than 0, then there is some n in the natural numbers such that 1 over n is less than epsilon. And again, we know that's true because this set of real numbers has some lower bound, and in fact a greatest lower bound, which is 0. So since epsilon is greater than 0, there must be some n in the natural numbers such that 1 over n is less than epsilon. So then if we say, okay, there is a rational number within any given distance, that's epsilon, of a real number, let's call it x, then we could think about the open interval x minus epsilon to x plus epsilon, and then we can do the proof above with these two things being real numbers, and there's going to be some rational number, m over n, between those two real numbers. So there is some rational number within any given distance, epsilon, of any real number, x. This property above is equivalent to saying that the rationals are dense in the reals, and we're going to generalize this idea to other spaces later on in the course.